The electromagnetic properties of plasma are fundamental to understanding magnetic fusion devices. Let's do a basic grade school demonstration. If I heat atoms of helium gas above their ionization energy with this Tesla coil, the electrons are freed from their atomic orbit, resulting in a hot cloud of helium ions and free electrons known as a plasma. Because all the particles have a net electrical charge, plasma is electrically conductive and magnetically controllable. When helion's electromagnets fire, they induce an electric current that flows in a loop inside the donut of plasma. As the current flows around the plasma, it generates its own reversed magnetic field which wraps the plasma. Rather than confining a plasma on an externally generated magnetic field like most other fusion approaches, in an FRC, the plasma is self-organized, held together by its own magnetic field.
And what it allows us to do is pretty unique. In an FRC, field reverse configuration, you can actually compress, heat, move, and translate that fusion fuel. And that's what we use to be able to actually make fusion faster and smaller.
After FRCs are formed on both ends, magnets fire sequentially, accelerating them towards each other at over 1 million miles per hour.
So much like squeezing a tube of toothpaste, it's called peristaltic acceleration. You increase the magnetic field behind the fusion fuel and it applies a pressure and that accelerates that plasma.
Electromagnets accelerate the FRCs out of the initial injector system into the main fusion compression chamber, where they merge to become one large unified FRC.
They actually collide into each other, superheating, converting all that kinetic energy, all that directed velocity into heat, into thermal energy, superheating the fusion fuel and getting it primed to begin compressing and getting fusion reactions out of it.
In the center of the device, the machine's magnetic field is rapidly increased, compressing the plasma with a powerful force over 10 Tesla.
One of the other unique things about a field reverse configuration is that it's high beta. And what that means is that it's high pressure. In a field reverse configuration, if you use a magnetic field to compress and heat your fusion fuel, think about squeezing a balloon. In a high beta plasma, which is very different from most fusion plasmas, the fuel pushes back on you. So as you compress that balloon, increasing temperature and pressure inside the balloon, it gets hotter, it gets more dense, and fusion starts.
During operation, the fusion core inside of Polaris will momentarily be the hottest place in the solar system. The plasma-facing materials that line the inside of a fusion device must be able to withstand thermal loads greater than a spaceship re-entering Earth's atmosphere.
Yeah, so the first wall is probably the most critical part of a fusion generator of any kind, where you have this core that's over 100 million degrees, and you can imagine any material next to that wall won't survive. It will melt.
However, the plasma doesn't touch the wall. Fusion systems operate under a vacuum, and the fusion core is insulated from the first wall by a vacuum boundary. But fusion puts off intense electromagnetic radiation, as well as high-energy neutrons that blast the wall with tremendous power, damaging even the most durable materials. The quest to find the perfect first wall is a key material science challenge in producing fusion power. At 100 million degrees Celsius, the deuterium and helium-3 atoms are moving fast enough. When they collide, they have enough energy to overcome their electrostatic repulsion and get close enough to fuse into helium-4. Helion's unique fusion fuels react in a manner that's particularly conducive to direct energy conversion. While most fusion power reactions release up to 80% of their energy in neutrons, deuterium-helium-3 fusion is aneutronic. When they fuse together, its energy release is carried by an alpha particle and one high-energy proton, no neutron.
The problem with a neutron is that it's not very useful in terms of actually generating energy. It just makes heat, where other particles are charged particles that you can directly extract electricity from.
All these fusion reactions within the plasma convert matter into new energy, which strengthens the plasma's magnetic field. As the plasma's magnetic field gets stronger, it pushes back on the magnetic field of the machine, causing a change in the machine's magnetic flux. This change in flux induces current in the machine's coils, which is directly recaptured as electricity and returned to the capacitors that originally charged the magnets around the machine.
So our goal is to compress and heat the fusion fuel right till it begins to ignite and then turn it off. Expand it, get that electricity out of the system, put in new fuel and repeat the process.
Helion's fusion generator needs a way to exhaust hot gases out of the fusion chamber after each pulse.
So think about the exhaust on your car. In the diverter is where we take the remaining fusion byproducts. Some have been burned, some fused, some unfused. We separate those. We also take the remaining energy that's out of the system and we extract that for electricity. And so it has to deal with some really complex engineering and physics, where it has the high temperature gas that's being exhausted from the fusion system. You actually want to then also pump out, you want to remove any air in the system in this exact same geometry.
After each 1 millisecond pulse, Helion's fusion electricity will be delivered to the grid.
What a pulse system really enables us to do is dial what we call rep rate. So I can change if you want to think about an engine, the RPM of that engine, so that I can turn up or down the power depending on what is needed for the load.
Helion's North Star is the delivery of commercial electricity to the grid as soon as possible. So, when does Helion expect to begin producing electricity, and how much will it cost? The availability of fusion fuels is a primary consideration for commercial fusion power, but the amount of fuel used for each pulse is minuscule. 500 milliliters of deuterium is enough for approximately 5.5 million pulses. Deuterium is abundant on Earth, but helium-3 is incredibly rare. It's even been suggested we'll need to mine it from the moon. Because the moon lacks a protective magnetic field like the Earth, solar winds create a buildup of helium-3 in the dust on the lunar surface.
Problem is that if going to the moon is part of your business plan, you already have a lot of challenges to making commercial electricity here on Earth. So to get helium-3, one thing Helion has done is we have patented a process to take deuterium, which is found in all water on Earth, clean and safe, fuse that together to make helium-3, then take another deuterium, fuse that together to make helium-4.